In this video, I want to look at the gamma distribution, which is very much related to the exponential distribution. If we have a Poisson process with mean lambda, we know that the waiting time until the first occurrence has an exponential distribution. The gamma distribution is going to denote the waiting time until the alphth occurrence, so maybe the second occurrence, or the fifth occurrence, the 67th occurrence, something like that. The CDF of the gamma distribution is given by capital F of x. This gives us the probability that my random distribution x is less than or equal to little x, is 1 minus the summation from k equal to 0 to alpha minus 1 of lambda x to the k e to the minus lambda x over k factorial. And this summation here, this comes from being 1 minus the probability of fewer than alpha occurrences. So the idea is we have a Poisson distribution with mean lambda x, and we're going to look at the chance that we have 0 occurrences, 1 occurrence, 2 occurrence, 3 occurrences up until alpha minus 1. That would be the chance that we do not get alpha occurrences, so we do 1 minus. Now that I have this CDF, I can start looking at the PDF, which is the derivative of this CDF. So we have little f of x. And if you work out the derivative of this summation and simplify, you get lambda times lambda x to the alpha minus 1 over alpha minus 1 factorial e to the minus lambda x. And any distribution with this type of PDF is a gamma distribution. So before I talk about the mean and the variance, I want to take a closer look at the gamma distribution, and also something very related, called the gamma function. The gamma function is denoted by a capital gamma of t. It's given by the integral from 0 to infinity of y to the t minus 1 e to the minus y dy for t greater than 0. I want to briefly consider what happens if t is greater than 1. In this case, I can use integration by parts to get negative y to the t minus 1, e to the minus y evaluated from 0 to infinity, plus the integral from 0 to the infinity, t minus 1, y to the t minus 2, e to the minus y dy. I can simplify this to get t minus 1 times the integral from 0 to infinity of y to the t minus 2 e to the minus y dy. Whenever I simplify this first part, I just end up with 0. And then this piece over here, I just factored out the t minus 1. So that's t minus 1 times the gamma function evaluated at t minus 1. So what this tells me is that gamma 6 is equal to 5 times gamma 5. And gamma 5 is equal to 4 times gamma 4. Gamma 4 is 3 times gamma 3. And you can continue this process to get that gamma of 6 is 5 factorial. In general, gamma n gives me n minus 1 factorial for integers. And this is only for n being a positive integer. Because of this, the gamma function is often called the generalized factorial. So now that I have the gamma function, I want to formally define the PDF of the gamma distribution and its characteristics. And in this case, theta is equal to 1 over lambda. And you can double check that this does have the appropriate properties to be the PDF of a gamma distribution, and that it is the same as the one we gave previously. And for this, my mean is going to be equal to alpha theta, and my variance is alpha theta squared. So let's look at some examples of using this. Let's suppose the number of customers per hour arriving at a shop follows a Poisson process with mean 20. So that is, if a minute is our time unit, then lambda is equal to 1/3, since it'll be 20 out of 60. What is the probability that the second customer arrives more than 5 minutes after the shop opens for the day? Well, in this case, we want the second customer, so we have alpha is equal to 2, and theta will be equal to 1 over lambda, or 3. So the probability of x greater than 5, if I want to use my PDF, probabilities using a PDF are given by integration, so I'm going to integrate from 5 to infinity, of x to the 2 minus 1, e to the negative x over theta, so negative x over 3, all over gamma of 2, and then theta to the alpha power, so 3 squared, dx. Well, I can simplify this, the integral from 5 to infinity of x e to the minus x over 3, and if I work out the denominator, I get 9. We can use integration by parts. When we do, we get 1 over 9 times negative 3x e to the negative x over 3 minus 9 e to the minus x over 3, evaluated between 5 and infinity. And if we work this out and simplify, we get 8 over 3 times e to the negative 5 over 3, which is approximately 0.504. So here's my probability. And since alpha is an integer, this is not the only way we could have done this. For the probability that x is greater than 5, we could have also used our CDF. This would have been 1 minus the probability that x is less than or equal to 5. And if we were to work this out, we would end up with the summation from 2 minus 1, well, from 0 to 2 minus 1, 5 over 3 to the k, e to the minus 5 over 3, over k factorial, which also ends up being 8 over 3 times e to the negative 5/3. So we do have our solution. Let's suppose telephone calls arrive at an office at a mean rate of lambda equal to 2 per minute, according to a Poisson process. We're going to let x denote the waiting time in minutes until the 5th call arrives. What are the mean and variance? In this case, alpha is equal to 5, and theta is 1 over lambda, so 1 over 2. The mean is then given by alpha theta, so 5 over 2. And the variance is alpha theta squared, so 5 over 4.